And I'm also very happy to be here. And thank you for the invitation to the QMAT meeting. It's amazing to see how condensed matter physics has grown in India. In fact, coincidentally, I was in the Chinese condensed matter physics meeting last month. And I think this one is a bit bigger. And dare I say it, more exciting work that I've heard about here. Anyway, okay, so thank you very much. All right, so as Brajesh said, I'll talk about strange metals, and the surprising and unexpected connection to black holes will be a small part of what I say. But as Brajesh said, you found my secret. Yes, a lot of us have indeed been working on the cuprate problem. And there was a time, I think, at a meeting like this, maybe 10, 15 years ago, that everyone was talking about cuprates. Now I seem to be one of the few, but still I think, it's still a very exciting problem. It's still the very best superconductor. We're learning a lot from topological materials and all the two-dimensional compounds. But I think even in the study of those materials, we're coming back to thinking about the cuprates, at least at the back of our minds. But I want to also show you that, in fact, there's been a lot of recent experiments on the cuprates, which are really, I think, advancing the frontier of the field. All right, so before I talk about strange metal, let me talk about, just briefly remind you of metals that are well understood, like copper and gold. And the theory of these metals really ultimately goes back to Boltzmann. He was thinking about classical gases, like the gas in this room. And he wrote down the famous equation called the Boltzmann equation, which describes collisions between molecules in the gas. And the success to his equation was the fact that the collisions are rare and statistically independent. And this is true because of the diluteness of the gas. And then Landau, much later, extended the same idea to electrons in a metal. Now, unlike the molecules in a gas, the electrons in a metal are very dense. So you wouldn't think that you could apply something as simple as Boltzmann equation. But in fact, you can, because collisions are, again, very rare. Even though the interactions may be strong, collisions, which say change the state of some particle, are rare because of the exclusion principle. So the exclusion principle comes in to save the day. And really that's really all you have to do, is to put the Fermi distribution function into the Boltzmann equation, and you have a theory that's really the foundation of everything in condensed matter physics, say before 1980. So one of the predictions of Boltzmann theory, and here also, this is the key point, in the Landau theory, you're neglecting any interference or correlation between successive collisions. You just assume they're independent of each other. And this is what we're going to try to put back in. Okay, so one of the predictions of Boltzmann theory, as extended by Landau, is that the scattering time, the collision time, the mean time between collisions, diverges as temperature goes to 0, as 1 over temperature squared. And this temperature squared just comes from application of the Pauli principle near the Fermi surface. So no matter how strong your interaction U, eventually, as temperature becomes very small, this becomes very long, and it's long enough for the collisions to be rare. And this leads to many predictions, including the fact that the resistivity of a metal increases as T squared. Sorry, there's an echo. Maybe I stand here. Okay. All right, so then you can ask, when is this going to fail? What is the limit at which this equation cannot work? And so if you think about the self-consistency of this, you find that there is a fundamental limit, which is now called the Planckian limit, that if the time tau, as long as the time tau is much bigger than the only time you can make out of Planck's constant and temperature, hence the Planckian time, which only involves fundamental constants of nature. As long as your time tau between collisions is bigger than this time, it's okay. And you notice this diverges as temperature goes to 0 as 1 over temperature. Well, this diverges as 1 over temperature squared. So no matter how strong your interactions, eventually tau is bigger than h bar over kT. And so the theory is fine. But I pointed out way back that this is a kind of a limiting time, and there are certain quantum critical states that we would like to understand better where this bound is realized. And I'm going to, of course, say much more about that. All right, so now now that I've explained all of condensed matter physics in a few words, really, that is the foundation of everything. Let's go to something much more mysterious, in the cuprates in particular. So as I briefly mentioned, one of the excitement in the cuprate field recently has been the application of this high temperature superconductor called yttrium barium copper oxide as a electromagnet to produce high magnetic fields in fusion machines. And there are many companies around the world, several in America and Europe and China, that are building big machines with YBCO. So the production of YBCO has now reached industrial scale. And so really this is something, there's no other superconductor where you could do something like this. All right, so this is the famous phase diagram of the high temperature superconductors. This is the temperature axis, and this is some axis where you're controlling the density of electrons in a copper oxygen plane here. I'll go into the details a bit later. Okay, so as you change the density by varying the oxygen concentration in this crystal, you get the high temperature superconductor up to a temperature of 100 Kelvin and even higher. And this is still the only material where you can do anything like this at atmospheric pressure. And you can hold it in your hand, and you can do an experiment in a classroom just with some liquid nitrogen with this material. There's no other material which you can do that now, even today. These were discovered in 1987. All right, so of course the big question is, why is that the case? Why is this the only material where TC is, say, above 100 Kelvin at atmospheric pressure? And that's the question we've been asking since 1987. I think we're closer to the answer, but we don't completely answer it. So obviously one of the questions you can ask is, if you want to estimate TC, the natural question is, what is above TC? Because whatever above TC is what's leading when you cool it to give you a superconductor. So if you look down here and you ask what's above TC, then you find what's called a Fermi liquid, where the Boltzmann theory I just summarized works perfectly fine. All right, but that's where TC is low. But when you look here, that's where this was a big surprise. Nobody predicted this. Nobody predicted these materials to begin with, and nobody predicted that they would show this strange metal. This was already seen in some detail in the 1990s, but has been studied a lot since then. So we have this strange metal where it's very clear to everyone, and that's one point that nobody disagrees, that Boltzmann theory doesn't really apply. Okay, so why doesn't it apply? Well, the most famous law is the linear dependence of the resistivity on temperature over a very long temperature range. And we saw several talks today talking about that in twisted bilayer graphene. But really, that's actually, the resistivity is kind of hard to interpret because it's theoretically a very difficult quantity to calculate properly. But a much nicer quantity is something you can get from the optical conductivity. So this is data on obtained from the reflectivity, infrared light reflectivity of this material. You're measuring the conductivity, sigma of omega, here, as a function of frequency of light. So these are the phase and magnitude. Now you can fit this result to this kind of generic form, and I won't go into detail where this comes from. It's a very general form, and it gives you a measuring this collision time tau. So that was very important in Boltzmann equation. So the collision time tau depends on frequency, and you can directly measure it. And what they found, as many theories had also indicated earlier, is this time obeys this remarkable formula, which is illustrated in this plot, that at low frequencies, where you think of f just some number, its time is exactly the Planckian time. So you have a relaxation on collision time that doesn't depend on the strength of the interactions. This is absolutely impossible in Boltzmann equation. In Boltzmann equation, the collision, as I showed you, depended on this coupling U, which is how strong the interactions are. And here, it disappears. So, and in fact, this kind of behavior is seen in many materials, in twisted bilayer graphene, in cuprates and pnictides, and so on, which have many, many different energy scales over several orders of magnitudes. But tau is just Planckian time. So that's a remarkable universality. There's a further universality of this as a function of omega over t. Okay. So this is really the heart, the key property of the strange metal that I'm going to focus on, more so than the resistivity. Okay, so this opens a number of questions that I will try to address. What is the origin of strange metal, and why is it ubiquitous in collateral electron materials? But as I said, the cuprates are very special. So many, many materials show the strange metal, but only the cuprates have such a high TC. So is there something different about the strange metal? I mean, if you look at most properties, they look very similar in many different materials. But what is really special about the strange metal in the whole loop cuprates that leads to the highest temperature superconductivity? So as Vijay said, that is the question that we want to answer. And I'll give you at least my ideas on that, if I have time. Okay. But as Brijesh also said, these were the kind of mundane questions that we were thinking about. But this has had a huge impact, if I may say so, on many other fields of physics. The progress, the techniques we've developed have impacted the theory of black holes and quantum error correction and so on. So it's sort of like Fermat's last theorem. It's great to solve it. Maybe someday we'll solve it. But along the way, a lot of beautiful mathematics has been discovered. Okay, so before I get to metals, let me say something about strange semi-metals, which are also Planckian, but are a little bit easier to understand. So what is a strange semi-metal? Well, of course, it's just graphene. So this was also actually a theoretical prediction. Graphene had been predicted theoretically to have this Dirac spectrum, this conical dispersion spectrum. And then it was found by Andre Geim and others. And then we argued in these papers that actually this material is going to be kind of strange. It's going to have very strong interaction, and the Boltzmann theory is not going to work. This happens because of some relativistic dispersion spectrum of pure graphene, where the Fermi level is right at the conical point. Through this framework, we said that the conductivity full conductivity should be a function of only frequency over temperature. So to have this Planckian dissipation here, but even the scale of the conductivity should be universal, quasi-universal. Anyway, so that was, I would say it was greeted with a lot of skepticism because people thought, well, graphene is just free electrons, and how can a strange metal appear here? But in this case, the theory was quite easy to work out once you had the right idea. And indeed, now there have been many experiments which are consistent with this. In fact, this is a microwave measurement of the optical conductivity, which shows exactly this type of scaling that we predicted. Very recently, in Arindam Ghosh's group in IISc, they measured the thermal conductivity and various other properties, and they see a strong violation of the Wiedemann-Franz law, which is another consequence of the Boltzmann equation, and in agreement with the theoretical predictions. And finally, one consequence of the strange metal behavior is that flow of current in graphene, or in fact in any, in this great graphene semi-metal, the flow of current is more like the flow of water than the flow of electrons in a metal. And this has been seen very beautifully in this experiment a few years back, where they've seen whirlpools of electrical current by these measurements. I won't go into details. And this is another consequence of this strange metal characteristics and the breakdown of quasi-particles in graphene. All right, so that's great. And this is, I think at this point, a reasonably, relatively well understood phenomenon. But it really is special to the relativistic structure of graphene. And that's what makes the analysis a lot simpler. Well, there's no such relativistic structure in the cuprates. The cuprates have a Fermi surface, as I'll show you in a minute, and you can't apply these theories there. And the other feature of the cuprates is that this strange metal behavior appears for a whole range of densities. So it's a compressible system where you can vary the density to anything you want, and you'll get a strange metal. But in this case, in graphene, this is only true very close to the direct point. So it's not a compressible, it's really a semi-metal for that reason. All right, so we want a model which is both compressible and has Planckian time dissipation. And that's the claim to fame for my favorite model, so let me describe it. I came up with this with my very first graduate student in 1993. It's a different version of it. Kitaev came up with the version I'll describe here. It has the same properties, and it's a lot easier to present. So that's the model I'm presenting. So here's it in the simplest form. Just imagine you have a bunch of sites, and you occupy some fraction of the sites with electrons. The most important properties are these are fermions. And now you're going to allow these fermions to move around. But normally, if you allow the fermions to move one by one with a single particle hopping, you will get ultimately something that obeys the Landau framework. But you put in a simple constraint, they can only move in pairs or in triples or so on. So for example, there's a process here where the fermion on site 11 and 12 hops to site 5 and 14, and so on. So every such process has associated with it a number, which is the amplitude for that tunneling event to happen. And so to specify the model, I have to give you a series of these numbers. Now, because this is an interacting electron model, you can think of each of these events as a collision. And these are all happening at the same time. And so this is leading to some kind of many-body entangled state. And you can't ignore the interference between all the processes. So if you try to put this on a computer, that's nearly impossible because the number of states goes exponentially. But what we pointed out was that already in 1993, that if you make a simple assumption that these numbers are uncorrelated random numbers, that are drawn from the same distribution. Actually, they could be drawn from different distributions too, but they're not correlated with each other. That's the most important thing. Once you make that assumption, you can actually solve this problem. And it's self-averaging, so any given sample will look the same. All right, so what do you get? So let me show you a little bit about technically how this is done. This is how you write it down in second quantized notation, where you have this random number, independent random numbers, u alpha, beta, gamma, delta. And if you know a little bit about Feynman graphs, you can actually do it in a few lines by just averaging graph by graph. So this is the usual Dyson equation, and this is the self-energy. And the self-energy is given by some expansion in u, which is this, u is the mean square value of this coupling. So basically, you write down various graphs, and you average them, and then you sum over all the free indices. And so what happens in a graph like this, which is called the Mellon graph, that there's sum over 3 indices and a factor of 1 over n cubed, so that this thing survives a large n limit. Whereas all other graphs don't survive. This vanishes as n goes to infinity. Of course, you can have these melons within melons within melons. So these are fully renormalized Green's function. And so there are the very simple equations you have to solve. So I wrote down these equations in 1992. I said, OK, maybe in a few weeks we'll solve them. Or somebody must have solved them. Nobody had. And we did get some properties in a few weeks, which we eventually published with some difficulty. I think today we have a much better understanding of the solution of these very simple-looking equations. And hiding inside these equations, believe it or not, is the structure of quantum gravity. Certainly in 1992, I had no clue that that was the case, but I'll try to indicate roughly where that comes from today. So if you want to fully solve these equations and understand the full structure of the asymptotic expansion, then you do need to understand some quantum gravity, amazingly. All right. However, what we did figure out already then is the leading terms at low frequency and temperature. And we found that there's no particle-like excitations left. And furthermore, there's some Planckian dynamics. That various response function only depends on frequency over temperature. So again, to emphasize how remarkable this is, from the point of view of Boltzmann equations, there's a coupling constant U here. The scattering time or the rate or the relaxation time of these systems do not depend on U. Only depends on temperature. Okay, so this is what it is, a solvable model of many particle entanglement in a metal. In a metal, because the density of the fermions can be anything you like. And it deals with a quantum state which has no particle-like excitation, no bosons, fermions, anyons, or any other particle you dreamed of. In fact, there are no particles at all. And the current is carried by some entangled quantum soup. So I wish I could describe it better, but that's really what we have. But it's good to have a solvable model where you can try out various things and test your intuition. Okay. And of course, as I said, it has this remarkable Planckian dissipation in various quantities that you can compute in this very simple looking model. Okay, so that of course got us excited. But everybody told us, you're crazy. How can you take this random hopping model and apply it to the cuprates? Well, I said, okay, wait a minute. Well, okay, now 20 years later, I think I can give some answers, which I'll try to give you some answer in that direction. Okay, but amazingly, it turned out that the first complete application of this model came in an entirely different field of physics. So let me try to say a little bit about that. So what are black holes? Well, these were discovered theoretically by Karl Schwarzschild in 1916, where he solved Einstein's equations of gravity and general relativity and found that there are solutions where light was trapped inside a horizon of radius r, where g is Newton's constant and c is the velocity of light. And if m is the mass of this object, if the mass m is the Earth's mass, this radius is 9 millimeters. So you'd have to squeeze the Earth to the size of a pea before it became a black hole. In fact, the density, the matter is even more dense, because once you form the black hole, the matter continues collapsing right to the center. And so you absolutely have to apply some theory of quantum gravity to understand what's going on in a black hole. So nobody believed this, but of course black holes are everywhere today. I don't have to go into that. And then we come to quantum mechanics of a black hole. So this was a subject started by Bekenstein and Hawking. And they show that black holes, when you think of them as quantum objects, are like black bodies with a temperature and an entropy. And the entropy that Hawking computed exactly is the area, proportional to the area of the black hole, and again, Newton's constant, h bar, and c. So this is one of the first formulae involving Newton's constant and h bar in a non-trivial way. Okay, so how do we understand this? Well, you can understand this from this, at least this is the picture that you often talk about, where you have some entangled pairs. So you have vacuum fluctuations, and you have an entangled pair of electrons or photons or whatever, and then one half of the entangled pair is inside, and the other half is outside. So the one that's inside will eventually fall in and be crushed forever, but the one that's outside could escape, and then an outside observer could see it. So the outside observer sees one half of an entangled pair. Now, of course, there's nothing special at the horizon. If you could be sitting at the horizon of some gigantic black hole today, and you would never know it. There's nothing special at the horizon, so the entanglement is still there. So this observer observed this electron, which is entangled with the other one, but the other one is lost forever since it's been ripped into the center of the black hole. So effectively, you only have a random qubit in your hand, because you have no access to its partner. And that randomness is entropy, which is what Boltzmann taught us. So that's a few-line summary of why black holes have entropy and a temperature. It has to do with entanglement on the surface. And this also explains why the entropy is proportional to the area, just like entanglement entropy, because it has to do with entangled pairs on the surface. All right, so that's been the canonical picture of black holes. Today we know that's not quite right. And in fact, for a certain class of black hole, well, before I get there, so why is this picture not right? So here I want to go back again and talk about what are called black hole quasi-normal modes. So for example, when two black holes merge, they eventually form a perfect sphere. And before they become a perfect sphere, they vibrate a little bit. And then, so there's some ringing down. And you can ask, what is that ring down time? So this was computed first by Vishweshwar, actually, before Hawking's work. And he came up with this answer for the ring down time of a black hole of mass m. So this is like a thermal relaxation time, because the black hole is a black body at some temperature. So this is the time it takes for it to relax. All right, so well, after Hawking came on the scene, he gave his expression for Hawking's temperature. And now you just do a very simple algebra, and you see the ring down time is exactly Planckian, where T is the Hawking temperature. Sorry, I'm missing an H there. So if you want to think of a black hole as a set of entangled qubits, these qubits can't be just pairwise entangled. They have to be entangled in a way that gives you Planckian dynamics. Okay? So therefore, a better picture of a black hole is something like an SYK model on the surface. It's not just pairwise entanglement, it's very complex entanglement, which can give you dynamics, which is Planckian. And this is something I noted. In fact, in 2010, I wrote a paper where this is the quote from the abstract, before anyone has even heard about the SYK. In fact, the SYK model didn't exist. I was talking about states of matter. The certain main field gapless spin liquids, what is now called SYK after Kitev entered the scene in 2015, realized the near horizon physics of charged black holes. So this is a detail I won't go into, but it turns out that for charged black hole, there's a simplification. So this looks like, a black hole in 3 dimensions, but it turns out that for charged black holes, you only need to worry about the radial direction and not the angular direction. So you can write down a theory of quantum gravity on the surface of a charged black hole. And then that theory reduces at low energy. It was known to many people in theory of quantum gravity, where you have one radial direction, which is space, and one time direction. And you can ignore the direction x. You just could take the zero angular momentum mode. So you get a theory of quantum gravity in one space and one time dimensions, which you derive from Einstein's equations. And do some path integral, Feynman path integral of Einstein action, take the low energy limit for this black hole solution, you get some theory. Amazingly, you can get exactly that theory by starting from taking the large N solution of the SYK model I showed you and looking at 1/n corrections. So there's 2 ways of deriving exactly the same theory. This was not done by me. This was done by Kitev and Marlesina Stanford. And it realized very explicitly the hope that I'd expressed in this paper 5 years earlier. OK, so what good is this? Well, it turns out from this, we finally have some new results about the density of quantum states at very low energies for any charged black hole in our universe. So Bekenstein and Hawking told us this was the entropy. And Boltzmann tells us the density of states is the exponential of the entropy. So that's the Bekenstein-Hawking factor. But what we now have is the energy dependence of the density of states. This is a new result, which was first obtained for the SYK model and then shown to be exactly applicable to charged black holes. So it's all reviewed in this paper for condensed matter physicists. All right, so that's really all I want to say about black holes. So it was a fun detour where suddenly this humble little model that we were struggling with had I would say a fairly significant impact on a totally different field of physics and really, in some ways, led to a lot of progress. I've only mentioned one, but many other progress on understanding the black hole information problem have been built on this understanding. Okay, but our original motivation was, for the SYK model, was to have something to do with the cuprates. So now the rest of my talk will be about the cuprates, and the time is what? Okay, I have about 20 minutes, I hope, since you have a 10-minute introduction, right? Okay, all right, so let's get back to the cuprates and give you an update. So for a few minutes, I'm going to not talk about the SYK model, even though it's my favorite model. But I'll talk about another favorite subject of mine, which is the subject of quantum phase transitions, but phase transitions in metals. And that's another valuable framework in which many, many different materials in correlated electron system can be understood. So here I show the phase diagram of this pnictide compound. It has a much lower TC, 30, 40 Kelvin. But it also has this phase here, spin density wave, which is basically a regime where the spins are in some staggered antiferromagnetic arrangement. And what you see here is, first of all, there's a strange metal, like in many, many materials. It's right where you have the maximum TC, like in many, many materials. But you also have that the spin density wave seems to vanish at some kind of quantum phase transitions here within the superconductor. So now the strange metal is a much bigger thing than the superconductivity. So let's simplify our life. And for now, just forget about the superconductivity. So I can draw this simplified phase diagram, on which books and articles and many, many papers have been written, where you imagine you have some metallic system which has a Fermi surface, which is called a Fermi liquid, and you have some parameter you're varying. And as a function of some parameter at some coupling SC, you develop some antiferromagnetism. So a certain set of spins form this antiferromagnetic structure. And in the simplest one-band model, this will reconstruct this Fermi surface, change the Fermi surface into something more complicated. So you have a quantum critical point here. And then above the critical point at finite temperature, the question is, do you get a strange metal? Can you understand, first, this non-Fermi liquid regime due to the presence of the zero temperature quantum critical point? And then next, understand the superconductivity, which is a lower temperature and a secondary phenomena, at least from this phase diagram. Okay, so that's the point of view I'm going to take. And for the, pnictide, this approach, I'm not going to say I'm the only one working. Many people have worked on it, and there's been a lot of progress. The issue of whether the fan is actually a strange metal is something I think only starting to be understood very recently, especially work by Avishkar Patel at ICTS. Okay, but let's go to the cuprates. The cuprates have a very different phase diagram. Here, this is the phase diagram as a function of P and temperature, which I showed you earlier. Here, the antiferromagnetism vanishes not at the best TC, but way down here. So, and people have studied this region of the superconductor very, very carefully over the years and never found any sign of a phase transition. Okay, there's always somebody in cuprates say, no, I found one. Well, even if you did, it was a very weak transition. Okay, so don't attack me. But there is no significant phase transition, which can change electron properties so dramatically to give you such a high TC or give you such a big strange metal regime. So there's no obvious phase transition within the superconductor. All right, so that immediately says you should just give up this idea of quantum phase transition and applying the cuprates. Well, not so. I'm going to argue, even though there's no evidence for a phase transition within the superconductor, there's significant evidence that have built up over the years for quantum transitions above between the two metals in the underlying normal state. So the picture is that there is some kind of hidden quantum criticality, which is very evident when you look at the metallic state, but the superconductivity eventually kind of hides it. I mean, the superconductivity is, of course, the elephant in the room we want to understand, but let's not worry about it for now. and just think about what's happening in the metal. Okay, so what are the various indications? So one of the first actually already came in the superconducting phase itself. So what you can do, and this is what Pratap talked about this morning, you apply a magnetic field and you see a vortex lattice, and you look at the local density of states in the cores of the vortices. And you see this very peculiar checkerboard structure. And there have been many such experiments, since this one in 2002 by the group of Seamus Davis and others. Okay, so, all right, so we know that in the core of the vortex, your superconductivity has gone away, and you're revealing the underlying normal state. So this was the first experiment telling you that there's some rather mysterious normal state in the core of a vortex, and presumably that mysterious normal state is somehow connected to this pink region over here. And I'll give you more experiments in this region in a few minutes. On the other hand, if you more recent experiments have looked over here, and there everything is fine. You get a certain peak at zero bias, which was theoretically predicted by just the conventional BCS theory of this type of superconductor. So there's clearly something going on in the superconductor in the core of the vortex, if not in the long distance property. So in the long distance, if you don't apply a magnetic field, the superconductor looks like nothing's changing. But if you look in the vortex, it looks like something is changing. And in the vortex, you're seeing the normal state. So really, it's the underlying normal state that's changing. Okay, so there's lots of indication of this in many, many observables in the normal state. For example, just measuring the Hall coefficient at low temperatures. So here you start out with an antiferromagnet, and P is the density of the vacancies in the antiferromagnet. But one very important thing to mention, when people say that this P is the doping, they mean doping with respect to the antiferromagnet. But a semiconductor physicist would always say the doping is with respect to the fill band for holes. And the fill band here has 2 electrons per site. So the density of holes in this system, from the point of view of a semiconductor physicist, is 1 plus P. So that's what you see in the Fermi liquid regime, but in this pink region, you don't see 1 plus P, you see P. And that's also another mysterious thing that we want to understand, if you want to understand the nature of the critical point. Okay, so I could go on. There's the STM data, which looks at the Fermi surface by quasi-particle interference. And at large P, you see this Fermi surface over here. And if you measure the area of where the holes are, this is the area where there are holes. That area is 1 plus P, which is the density of holes, divided by 8. Why you divide by 8? Well, a factor of 2 for spin. And there are 4 quadrants. So if you take that, you'll get the total number of holes here in this region, including the full circle like this, would be 1 plus P after accounting for spin. So that, in fact, agrees with another very fundamental theorem of solid-state physics, which is the Luttinger theorem, that the area enclosed by the Fermi surface is independent of the strength of the interactions, which is also very remarkable, but it's a theorem for a Fermi liquid. But if you looked at this pink region, then what they said is if you looked at the area of this green region, just by hand, they cut it off at the Brillouin zone boundary, they got an answer very close to P. So the area of this green region should be P over 8. Okay, so this is another angle-dependent magnetoresistance measurement. Again, I won't go into the details. You apply a magnetic field in this direction, in some strange angle, and you measure the resistance in this direction. And so the electrons undergo this very strange orbit, and you can understand what's going on, provided you assume that there's coherent motion of electrons on this strange orbit, meaning that they have to move coherently between layers. And that shows, again, a very clear phase transition between 2 very different observers, one with the large Fermi surface and one with some small Hope pockets. So anyway, so what is going on? So our proposal was that this region is the state we call FL star. And let me just give you very quickly a picture of what this FL star is. So this was our statement in 2003 that there can be states of matter that violate the Luttinger theorem. And these states require a very subtle type of entanglement, which is quite different from the entanglement in the SYK model. And I'll show you what it looks like. And it gives you a total area of the enclosed by the Fermi surface is not the density rho, but rho minus 1. And if you have 4 pockets, the area for a pocket should be p over 8, which is exactly the area that at least in a sort of the ad hoc manner, the STM measurement was measuring here. Okay. All right, so let me give you a simple picture of what this is. So here I want to start with this famous resonating valence bond state of Bhaskaran and Anderson, where you imagine in the insulator, where you imagine that the spins form these singlets, and the singlets resonate in many different configurations. But we want to remove some electrons. We want to dope the system. And you dope them by removing electrons here, and you get these vacancies, which we call holons, and also an unpaired spin, which we call spin-ons. So now you can have these spin-ons and holons moving independently of each other. So those are fractionalized particles, which in one case, carry charge but no spin, or they carry spin but no charge. And much of the work in the early days in the cuprates was thinking about the dynamics of these materials as an origin of understanding this mysterious pink region in the phase diagram. Well, so the recent experiment I showed you, in particular this one here, where you have coherent transport along this axis, even at low doping, tells you that this can't work because these holons cannot tunnel from one layer to the next. Only all electrons can go from one layer to the next because these are fractionalized particles that only make sense within this entangled state in a given layer. But this is actually quite easily fixed. You can imagine that there's some attractive interaction between holons and spin-ons, and then they can form a bound state, which are these green dimers, and then the whole thing can resonate. So you have these bound states moving around, and these bound states have exactly the quantum numbers of an electron, and they'll form a Fermi surface. And so this is a very simple construction, at least by waving your hands a lot, of a metallic state that has, with the Fermi surface is enclosed, a non-Luttinger area, and our prediction was p over 8. Okay, so I'm continuing this detour, but I'll come back to the main topic. So what's been very exciting is that just last year, there's this beautiful measurement of what's called the Yamaji effect, which is another version of this ADMR experiment, but in this particular compound with a special crystal structure. And what they see is a peak in this resistance along the C-axis, and that peak allows them to read off the size of the pocket. So this is the first real actual measurement of a Fermi pocket in this underdoped region. And they came up with an answer in the abstract, 1.3% of the Brillouin zone. Well, the doping P is 0.1, and I've just argued that in an FL state, the area should be P over 8, and that's very close to what they observed. So we're pretty excited by this, and I think this gives fairly strong evidence that there is a whole new metallic state present in the left. So now for the cuprates, I can draw the same phase diagram, at least globally, that I drew for the pnictides, except this phase transition is much, much more subtle. Here we just have free fermions, roughly speaking, and here you don't have a broken symmetry like antiferromagnetism or whatever. You instead have entanglement, or you have a spin liquid physics, where you should really think about this state as, roughly speaking, as a bunch of singlets and these green extended objects resonating with each other to give you a metallic state with these Fermi surfaces that violate the Luttinger theorem. Okay, so we've done a lot of work on understanding how you go from this to the superconductor, but I don't want to go into that. So let me get to the final part of my talk, is put everything together, all right? So what we can say is that for essentially every material that we know of, which has a correlated electron superconductor, there is this kind of universal phase diagram. You have the ordinary metal state here, where Boltzmann, Landau, everybody, Luttinger, everybody is happy. And then you have some other state here. You could have a broken symmetry, in which case, again, Boltzmann, Landau, and Luttinger are also happy. Or you could have a state with just this FL star state, which doesn't have a broken symmetry, but it has some emergent gauge fields. So there, again, Boltzmann and Landau will be happy in some restricted sense, but Luttinger will be totally unhappy, because Luttinger would not be satisfied. So those are the two types of possibilities. And we can write down some general theory for them. And in all cases, they involve a Fermi surface coupled to some scalar field, which I call phi, which could be in broken symmetry or a Higgs field. And you can try to study that. And so this is, in the simplest framework, this is what's called the Hertz-Millis theory for the case of broken symmetry. So one of the other things we have realized in recent years is that this theory on its own simply cannot give you a strange metal. And I won't go into the details of that. It has to do with the momentum conservation and some of the effects we learned when we studied the graphene semi-metal. Okay, so what you have to put in something that breaks translational symmetry of a perfect crystal. And the most important thing you have to put in is the fact that this critical point, the value of this coupling S can be at different positions in different parts of the sample. One part could be the left, one part could be the right. That's a ubiquitous feature in any real material, unless you grow them extremely carefully. And that turns out to be the key thing you have to put in. All right, so now you have to write down a theory for a quantum phase transition between two metals in the presence of this disorder. Okay, so that's the problem that we made a lot of progress on, starting with this paper with Avishkar as the first author. And that's where all the insights we built up over the years from the SYK model really came in to help us. So in the last few minutes, let me just tell you what that theory is. But to summarize, the whole interlude on FL star was simply to, from this point of view, was to show you that there's a huge amount of experimental evidence that there's indeed two different metals in the two sides of the cuprates, even though there's no broken symmetry. And they differ in a very big way. The Fermi surface is totally different. It's not some subtle parity broken or something. It's a very big difference, and it all has to do with entanglement, not with broken symmetry. Okay, once you have two metals, then life becomes easy. You can just do a theory of the critical point by the usual tricks. But here, the model that really came in to help us was what people are now calling the Yukawa SYK model. So this is very similar to the SYK model. It's a solvable model where you had a whole bunch of fermions hopping randomly between n sides. Here you have both fermions and bosons. So the fermions have all the same energy, psi, and you have a bunch of harmonic oscillators with the same frequency, omega 0. And then you have this Yukawa coupling, G, but the only thing, these are all independent random numbers. So this is also a model you can solve by very similar methods to the SYK model, and you get the same answers. You get some universal Planckian dissipation and a quantum state with no particle-like excitations. So this is an equally good model that we could have started. The whole history would have been different if people had looked at this model first. This turns out to be much nicer in terms of thinking about a real two-dimensional metal. Okay, so this is so I'll get a little bit technical and I'll then summarize. This is the kind of theory you have to look at. You have a Fermi surface of the electrons. So now we have to take this model here, to something realistic. So you have to make these fermions disperse in 2 dimensions. You also have to make this disperse in 2 dimensions. And then you have to make this a local function of position. So we do all of that. Here's the fermions dispersing with the Fermi surface. There's some Landau-Ginzburg theory for phi. And then in blue are everything is local in space. And then blue are the random functions of positions. So this is a very complicated theory, and we are starting to understand more and more about this through various methods, including a lot of numerical work that Avishkar has been doing. But you can understand the basic things at somewhat higher temperatures by just taking your SYK tricks and applying it to this model. So basically, we take exactly the same tricks I showed you at the very beginning, You just expand the graph and do things to order by order by adding some extra indices to make the large n limit work. And you get these sets of equations which you can then solve. And when you do that, you get really a lot of very encouraging results. You get resistivity which is linear in T in this region here. This is the superconducting instability. This is the Fermi liquid region. This is the strange metal region. We're only to the right of the critical point. And we get this optical conductivity relaxation time, which looks very, very similar to the observations. So this is the theory. This is the experiment. OK. In this very simple model and solving those equations correctly for the transport properties. All right. So am I on time? OK, great. So let me recap. I've gone through many, many things here. But let's try to summarize in a few minutes. OK, the hero of the story, of course, is the SYK model. And it describes, it's amazing to get a model that describes multi-particle quantum entanglement, where you lose all particles and you get Planckian dynamics. And also, some people say strong many-body chaos. So, you might think that, they have all these solvable models by the Bethe ansatz in one dimension. But none of those have this property. They all have an infinite number of conservation laws, and they don't thermalize completely. In fact, they take forever to thermalize. This one thermalizes in the shortest possible time. So it's the exact opposite of integrability. And the amazing thing is that you can still solve it, at least for certain properties. You can't get the full spectrum like you can for integrable models, but you can do really essentially all you need for any realistic experiment. OK, so this model, as I've tried to show you in the second part of my talk, that there's a two-dimensional realization of this model, which people are now calling the 2D YSYK. It yields a universal theory of strange metal arising from quantum phase transition metals in the presence of this tuning parameter, sometimes called the Harris disorder. So that's how you get a strange metal. And for the cuprates, really there is something special. So it's not the strange metal that's special for the cuprates. It's what to the left. It's this FL star. The fact that this phase transition is, if you sense it's a transition more in the entanglement than in a broken symmetry. That's what's really unique to the cuprates. And that's what leads to this antiferromagnetism as being over here rather than being over there. So it's very tempting to say that is the reason it has the highest TC. I think it is, but I have not established it. So that's a question that we're still working on. But there's definitely something unique about the cuprates, and that is the existence of the spin liquid physics in the pink region, something that Bhaskar has also been saying for many years. OK. Anyway, so this same theory, however, the theory of the strange metal doesn't care that much, it turns out, fortunately. And this is consistent with experiments. I mean, strange metal is seen in so many materials. The FL star is only seen in the cuprates. And in our theory, they have essentially the same behavior, at least in the strange metal regime. So that's encouraging. And finally, I said very briefly, amazingly, this kind of quantum chaos, chaotic entanglement that's present in the SYK model also seems to be present in a large class of black holes with a net charge. So, and that picture is also very different from the one that came out from string theory, which only looked at supersymmetric black holes. All right, thank you very much.
Thank you very much, Subir, for such a wonderful, engaging talk.
Sure.
And I think we can take up a few questions. So, one there.
So, thank you, Professor, for this interesting talk.
Thank you.
I have a very general perspective question.
Yeah.
From 1908, when this first superconductor was discovered, after that, 1986, this high-DC cuprates was discovered. 1979, this heavy fermion superconductor was discovered. And then 2007, basically, pink-type superconductor came on the scene. And all of the superconductor came on the scene is basically it's like a kind of accidental, experimental discovery, or most of it, at least I am aware of.
Yeah.
So
So nature is much smarter than us theorists.
Yeah. So the thing is, what is actually I want to ask or want to know that are you in a stage now in 2026 that we can predict a material even with the help of AI that can really predict some kind of outstanding superconductor that will solve the energy problem?
That's the dream. No, I would say the honest answer is not no, but hopefully in my lifetime. I think we're getting there. Like I said, even for the cuprates, nobody is close to actually computing the value of TC. Forget about computing the value of TC. Understanding why is it that in the cuprates the number is so much higher than anything else. Even just qualitatively understanding why is it more in cuprates as opposed to the pnictides? Why is it more on the hole doped cuprates and not the electron doped cuprates? I think we have a lot of phenomenological hints, but from the point of view of basic theory, we can't answer those questions. Is there some other material that AI will discover? I wouldn't rule it out. I mean, people are putting a lot of money in companies that would think will do just that. It's looking at a whole bunch of data out there, and maybe, but there are some deep conceptual questions here. I think that AI will not will not get, because it's just. So I think there are some further conceptual leaps that are needed, and let's see where they come from. But it is humbling. But I will say that if you take out the cuprates and some of these other things, in many other contexts, the same methods have predicted all kinds of things. This has been the whole framework of condensed matter physics has been incredibly successful. Here, perhaps less so, but these are the most challenging problems, I think.
Very enlightening talk. My question is probably a very mundane one. In these green objects coexisting with the valence bonds, why is the relative phase plus? Is there a specific reason for that?
Yes. Okay, that was very quick, but very observant of you. I didn't really emphasize that. Yeah, so you're asking why this is plus.
Yeah, like a triplet.
No, it's not a triplet.
It's not, of course, it's not.
It's so what's happening in the green object is this hopping back and forth. So that's just an electron hopping. So the hopping matrix element is minus T, because it's minus T. It's just a bonding orbital. I mean, it's a two-level system, and so this is a very simple picture of the hole-on and spin-on binding on just a single bond. I'm not saying this is the real thing. To do the real thing, you have to have a theory of a real spin liquid, and the green objects are all extended, the bonds are all extended. In fact, there's gapless points. We're working on that very hard. I just didn't have time to show it. So there's a much more complicated theory. But this gives you, the thing about this result here, and of the Latin, so as we said, that there are these Fermi surfaces which must satisfy this quantized relation, that you remove exactly one from the density. So when you have something that's quantized, as this is very familiar in topological physics, if somebody gives you this particular band structure must have some topological quantization, you say, well, let me just take the simplest possible band structure which has exactly flat bands and which has the same feature. There's something similar here. There's a topological relation. So if you want to understand the topological relation, you take the very simplest model that shows it. And this is the simplest model that shows it. But I do not mean to imply that the cuprates look anything like this. If it was this simple, we would solve the problem.
And so very inspiring talk as always. So you alluded to to this STM data on the normal state cores of the vortex lattice as being indicative of the normal state, and these density waves as being part of the normal state. You also alluded to the normal state being a FL star, and there is a transition. But in the experiments at very high fields, where you can kill the superconductivity to see the actual normal state at high fields, it was my reading of the experiment that they saw a glass that was Avishkar starting point. What is missing in the experiments that they don't see these density waves and FL stars that you think of as the starting point for this theory?
Okay, so that's all very good questions. And answering those questions are exactly what we've been working on for the past decade. So let me give a very quick answer. So FL star is really the higher temperature state. I mean, we define it as a zero temperature state, but in the cuprates, it's always unstable. Maybe in some other universe, it'll be stable down to zero temperature, and then we would. But FL star is a state at these higher temperatures here. And it's precise. So this experiment I went through very quickly. Yeah, so this experiment, this Yamaji effect experiment, is also done above TC. Okay, it's done at these higher temperatures. So there is, at this temperature, there is no sign of charge density wave order or anything like that. What you were referring to was experiments done down here at low temperatures. And there you see something, there you do see the charge density wave order at very low temperatures, even in the same material. So there are some low temperature states which are, in the end, conventional, in the sense that they can be understood by some Hartree-Fock theory, the superconductor or the charge density wave. But the difference between the superconductor here or the charge density wave, where is the phase diagram? Yeah, so the difference between, so the superconductor here and the superconductor here are the same. The charge density wave here is also fairly conventional, but the normal state here and the normal state here are totally different. So it's the onset of superconductivity that's different. The superconductor itself is pretty much the same, except when you open it up by looking at a vortex. Then it's different. Okay. And all of this, we have computed all of these features in many different papers.
Yes, my question is with regard to black holes.
Yes.
And quantum entanglement. So here, what are the quantum particles you are referring to, and what are the quantum states involved with regard to black holes? And if it is one of the constituting proton, then how much opportunity it gives sitting on Earth to monitor black holes?
Okay, great questions. So let's see. So I gave this picture saying there's SYK models around a black hole. Of course, this is not to be taken literally. So it turns out that what's understood from the SYK model, that there's certain features of black holes that are universal, that is independent of the particle content of the universe, for example. So one of them is, of course, Hawking himself discovered this expression here for the entropy of a black hole. He didn't need to say, it was a very general expression. It didn't depend on anything. It didn't, whether neutrinos or whether there's dark matter, it doesn't matter. This is the same answer. Okay. And what we've shown now with many people, shown now that is more that's universal. There's the cinch factor that also doesn't depend on anything. So things are more universal than Hawking thought. So this energy dependence is very universal. But then there's this thing here, the strange number 347/90. That's the only number that depends on the particle content of the universe. And that's, this paper by Ilyas Murthy and Toriachi. And Ashok Sen did very important work on contributions to computing this kind of number here. So here we really need to know what's in the universe. I don't know. This is their calculation. But the rest of the expression is universal. That's why the title of my talk was Universal Theory of Black Holes. So there's quite a bit that's universal. So once something is universal, the lesson is you try to compute it in the simplest possible way. And that is what the SYK model is.
Another question?
Is there a reason why we always see the left of the quantum critical fan and not the right one?
No.
Because in terms of some symmetry breaking at each star and not the right one.
I don't know. I mean, in the NICTAD, you certainly see both sides. But that theoretical calculation was because we were just lazy. I mean, it was much harder to do the calculation on the left. We didn't do it in that paper. But Avishkar has done both sides, I think. Well, here they see both sides.
But in terms of T star, we see some symmetry breaking happening, and universal symmetry, but there is nothing happening in the right hand side.
Oh, well, okay. You mean this, where's the right-hand side of this? Well, there is something happening with the quasi-particles. The point is that here you have this large Fermi surface. In the strange metal, you also have the large Fermi surface. So the change is much more gentle. The Fermi surface is remaining the same. It's just becoming fuzzier. So it's hard for people to say, okay, I don't know. Yeah, I mean, I guess ZX Chen and others have argued maybe it's a first-order transition or something. I mean, you also see this in the Seamus-Davis data. That was at low temperatures, but you see this here. No, that's up ahead, sorry. Yeah, here we go. So, you see for certain dopings, for the small dopings, you see these arcs, and then suddenly it goes from an arc to the full thing. But the point is that on the left-hand side here, there's a much more dramatic difference from the strange metal. The strange metal has the big Fermi surface. Okay, so it's easy to identify even on the Fermi surface. It's easy to identify, this line from looking at the change to the left-hand side as over here, or by doing the magnetotransport measurement. But going from here to here is a much more gentle phenomenon. Like, that would be my thought, but okay. Yeah.
Fantastic explanation. Talk about zeros of Green's function in Joe Martin's.
Oh, great. Okay.
So maybe that's changing across the zeros that disappearing.
Yes. So, okay, I have a whole other talk on that. Yeah. So, right. So these, to understand this Fermi surface, and I don't have the slides here, but I had to pick them out too. So there's very important work by YRZ, Maurice Rice, and Fuchen Zhang, and many others, Felic, who have tried to get some pseudo-gap state using zeros of Green's functions. So, I mean, I think that's very important work. But I would understand the same structure in a different way. And I think that may get the Fermi surface correct, but it will not get the full excitation spectrum and the fractionalization structure correct. Okay, and so what I would say is that if you have a zero of a Green's function, it means your self-energy is infinite. Okay, so the self-energy is infinite, it means you're not doing the right theory, because the self-energy is not a physical quantity. The self-energy is just telling you what the deviation from your bare assumed Green's function is. So you have to take a separate bare Green's function to get finite self-energy. That's the only way to work. So what you have to do to that theory, and we've shown how to do that, is you have to introduce fractionalization in the proper way. And once you have the right set of fractionalized fields, you will get the same Fermi surface, but you will also get, and you will not have any zeros anywhere, but you will also get the full spectrum and a better understanding of the state. So I would say YRZ, we're also talking about FL star, but it's not a complete theory. Yeah. And that's what I would say. Also, I would say that our FL star paper was a bit earlier than the YRZ paper.
Any other question, comment? Just one small sort of observation. I mean, the SYK model, perhaps the only model which gives you an insight about the interior of black holes?
I mean, the whole class of models, SYK-like models. It could be the Yukawa SYK model. For black holes, it doesn't matter which one you take. Yeah.
But it's also, for example, a model for strain metal, strongly correlated state of permanence. So my feeling is, and in fact, your model is rather, you have interactions which are all random, and then you average them out. So could we sort of summarize, or I mean, not summarize, but rather, is it pointing to a universal sort of situation where under extreme conditions, be the extreme gravity, be it extreme correlation, the details of interaction, details of hopping, so all these things become irrelevant. So what remains is the SYK. So can I say that is SYK or SYK-like paradigm model is the universal state of matter in any extreme conditions?
Well, at least when you don't have quasi-particles. I mean, it's a starting point.
No, but extreme conditions.
Well, I mean, you would say that the FL star is not described by SYK. FL star is it's spin liquid. It's a different type of it. There are many types of complex entanglement. Yeah. So when you get complex, the Laughlin state has complex entanglement. Various spin liquid states have complex entanglement. But those states have fractionalized particles. They have emergent gauge field with fractionalized particles. So we want to now understand states where there are no fractionalized particles or anything at all. And in fact, the simplest such states are strongly interacting conformal field theories in high dimensions, but those are not compressible and not easy to solve. So the SYK model is like the simplest model which has all these features. And that allows us to very efficiently extract certain universal features of black holes, for example. So there's, the connection between SYK and black hole is actually stronger than between SYK and strange metals in the end. Because in strange metal, you do have to go to 2 dimensions. See, what I showed here for black holes way back when was that you only needed a theory of quantum gravity in one space and one time dimensions. And that's what makes the connection to SYK very, very explicit. Yeah, here. It's only, there's an ADS2 structure. There's no ADS2 structure in strange metal. So we really had to make, had to search for how to do it. And there, the Yukawa SYK model was the right starting point. Yeah, so for strange metals, you should start from Yukawa SYK. That's what we've learned. But for black holes, you can start with either. Black holes are in some sense more universal, at least at low energies.
Thank you very much, Subir. I think maybe one more.
Between yesterday and today, we heard about 2 different paradigms for understanding topologically ordered states of matter, right? You talked largely about fractionalization.
My FL star story, yes.
Yes, about fractionalization in FL star. And Professor Jain told us in great detail about composite fermions.
Yeah.
Is there a way to understand topologically ordered states of matter like the FL star using the language of complementary language of composite fermions?
Well, I mean, the way, that's a good question. I mean, first of all, this is a compressible state with the Fermi surface. I mean, also there are compressible states of composite fermions. I think there certainly are connections. So one connection is just the part-on approach. The part-on approach, I think, is what allows you to talk about even FL star and also composite.
Part-on is fractionalization.
Yeah, well, okay, but it's the part-on route. I mean, I'm a composite, okay. Yeah, the composite fermion it can also be thought on in a part-on construction, as Jain himself has shown. For us, we use the ancilla picture, and the ancilla picture is a little bit different from part-on. So, in the sense of the if I take the effective low-energy theory rather than the mechanism of how I get it from some microscopic model, but look at the effective low-energy theory. In all cases, you have some bunch of fractionalized particles, you have some gauge fields, and they're interacting with some set of rules. That's certainly common for both.
Is there a Laughlin-like wave function for FL?
No. Well, I think the closest you would get for a simple wave function is precisely this fermionic dimer model. That's our best. And in fact, there is actually a beautiful paper by Matthias Punk. This model here, this fermionic dimer model. There's a paper by Matthias Punk where even at finite density, it's sort of like an RK point where you get an exact solution of FL star. Yeah.
So I think it's time to close this session. It has been a very engaging talk. Thank you, Subir, once again.
Thank you.
And, my friend Satyavrat has something for you to.
Oh my God.
This is.
Oh my God. Okay, thank you. Wow. Thank you very much.
Krishna for many of us.
Krishna and Arjun. Oh, okay, all right.
Krishna for many of us. Thank you.
Thank you. Thank you. Okay.